Yeah, yeah. Welcome back. Sunday we have a revised schedule. Now we'll complete this class before 5. You expressed a worry that whether I'll be completing the entire syllabus of heat transfer within a given time. Uh, this class is up to 22nd. Probably we can complete because we are already into convection heat transfer, and after this we have you know the condensation and boiling topic to be covered, and heat exchanges, radiation heat transfer. So I'll try my best to cover all the topics within the time schedule given to me. And someone said, what is the important? What is a thermocouple, and why are we using in HT subject? See, thermocouple is a device used to measure the temperature. I have told you already. I think it works on Seebeck effect. And instead of a thermometer, to remember, we all are fully aware of thermometer. Thermometer is used to measure the temperature, right? Now, similar such device with a dynamic response. See, when temperature, I told you, the temperature of the fluid continuously changes in many mechanical engineering applications. When fluid temperature is very quickly changing from millisecond to millisecond, then your thermocouple should be in a position to measure the temperature. And the principle of measuring the temperature using a thermocouple, yesterday I explained, it is Seebeck effect, and the temperature difference causes the EMF effect, EMF induced in the circuit, and the EMF is calibrated to record your temperature. Now, why we use this thermocouple? That's where I said T minus T infinity divided by Ti minus T infinity is equal to e to the power of minus HAT divided by rho Cp. The temperature distribution equation of a lumped body can be used to define a time constant of a thermocouple, and that's where I use the concept of reducing the initial temperature difference by 63.2%. So the concepts of heat transfer, wherever it can be applied, be it measuring device or a practical application, always apply. So don't get confused, and if you are already a final year student, you must have definitely gone through your heat transfer laboratory experiments and that you see. So thermocouple is very much connected to heat transfer, because without thermocouple you cannot measure the temperatures, and therefore it is very much relevant. Don't think that I'm talking instrumentation here. The cryogenics and its applications, the low temperatures. In fact, low temperature altogether is a different science, and you all hear about the cryogenic engines used in satellite launching vehicles. India's indigenous capacity to develop. So, with this simple clarifications, there is nothing much. Someone is asking for the previous lectures, links to the previous lectures. Maybe I request you to contact JNTU authorities or the convener at the JNTU Anantapur. I think he should be in a position to provide you with all such information. And these questions and all, maybe today I will upload. And we very quickly come to this assertion and reason, where we had a little confusion yesterday. Let me take up that. In a liquid to gas heat exchanger, fins are provided on the gas side. So a statement is given in a liquid to gas heat exchanger. I told you a typical application of car radiator, where the water circulated through the engine jockets reach the header of the radiator. From there it dribbles down to the bottom header, lower temperature header, and in between, as the water dribbles down through the tubes, the air is it's a cross flow heat exchanger. When water is coming down from top header to bottom header vertically upwards, horizontal airflow is expected, and when horizontal airflow moves across this tube surface. And here, those fins, if you have seen, the radiator fins, they're very closely packed. The gap between them is quite smaller. And therefore, in all such cases, gas flowability is very high. And therefore, between the spaces, in fact, I was explaining to you about the boundary layers formed between two adjacent fins, and the gap should be sufficiently long. And when you are using liquids, the boundary layer thickness is very, very high. And therefore, when you use liquids as a convection medium, the gap between the fins should be very high, so that fluids can very easily flow between the fins and come out. When you talk about the viscosity, a parameter like viscosity is normally high for liquids as compared to gases. So the viscous effects are more, and therefore boundary layer thickness is more. And by all means, when we talk about appears to be true, and it is true too, the gas offers less thermal resistance than liquid. Yes, because the thermal resistance, when we talk about it, it's convection heat transfer coefficient. So convection heat transfer coefficient, H, is a function of thermal conductivity also. Like I was slightly touching upon, when you have a plate on which the fluid is moving, the first layer of fluid, initially comes to a no-slip condition, meaning the molecules get deposited on the plate straight away. And absolutely they don't move because of the heterogeneous friction or wall friction, whatever I said. So when the molecules are sitting pretty on the solid, the mode of heat transfer that happening, and therefore the convection heat transfer comes into play. Now the convection heat transfer again is a function of thermal conductivity. Thermal conductivity of the gases are low, and therefore the thermal resistance is very high for the gases, whereas it is mentioned less. That was the confusion. So when you look at it, both A and R individually true. A is true, but B is not true, because it has more thermal resistance because of lower heat convection capabilities right in the first layer. So both A and R individually true. Again, it's not correct, because A is correct, whereas B is not correct, because gases offer more thermal resistance than liquids. Please remember that. And therefore, A is true, but R is false is the correct answer. That's where we went a little. And we normally in heat transfer parlance, we call it as wetting of the surface. So the fluid, when it goes, the wetting nature of the fluid to the surface is very, very high, and therefore we go for that. So with that small clarification, we will move on to convection heat transfer. So very briefly, we were discussing, I just started discussing about convection heat transfer. Okay, convection involves fluid motion as well as heat conduction. Both the things parallelly happen. See, when I said heat transfer is because of the bulk motion of the molecules. So molecule is going to the hotspot picking up heat is one, and molecule en route as it is coming up may get a chance to collide with the rest of the molecules, because they are many in number, and the random motion of the molecules mandate, rather necessitate a collision. Collision is obvious, and therefore collision happens. Whenever collision happens, momentum exchange takes place, and that's what we have. Convection heat transfer obviously dominates, but to a limited extent, convection heat transfer also takes place. So heat transfer through solids of the with high viscous fluids and liquid metals, where when I talk about liquidity is very, very less, meaning the molecules cannot very freely move around. So for liquid metals, the thermal conduction is very, very high, whereas convection is very less. So is the case with viscous fluids. Very viscous fluids like lubricating oils, this molecular movement is not very vigorous and very easy within the medium, and therefore the movement of the molecules by virtue of temperature difference, you call it, or because of the flowability, you cannot ensure all the molecules come to the hot spot. Therefore, conduction and convection both needed to be discussed in certain cases. Only in certain cases, like I said, high viscous fluids and liquid metals, the conduction also will be a predominant factor. So, when we talk about convection heat transfer, please don't ignore the fact that conduction also prevails to a limited extent. Okay. Color plates, and one can be hot, another can be cold, and therefore heat transfer effectively is from hot plate to the cold floor, and there will be rigorous movement of the molecules from hot plate to the cold plate. It depends on whether you are for that. And here the velocity gradient, we did discuss about it, and towards the end of the last. So, the essential difference I was talking was that the fluid, just before hitting of the plate, it was completely at free stream velocity, at the same uniform velocity it was coming. But when once it comes onto the plate, solid zone, obviously the flow pattern is slightly disturbed. Particularly, I was explaining using that diagram. Particularly when fluid flows in the immediate vicinity of the solid plate, the frictional effects cause the velocity to vary immediately, right on the solid boundary. But after certain y distance, the x and y are mentioned here. X is the fluid flow direction, y is the normal direction to the plate or a solid boundary on which the fluid is flowing. So along the y direction to a limited distance, the velocities keep changing the free stream velocity, because that was the velocity with which the fluid was approaching. And until otherwise I create a mechanism or device to enhance the velocity, I expect the fluid to flow with the same velocity if the pressure difference is properly maintained. So the velocity variations we have discussed in the last class. So, the convection heat transfer, I was just explaining while explaining the assertion and the reason question, the logic. I said initially in fluids, particularly where there is a solid boundary associated in the convection heat transfer, when the fluid is flowing, the fluid gets deposited on the plate and no surface condition, no slip condition. So, maybe if you want me to draw this, the same diagram what I have drawn yesterday. The no slip condition, the fluid molecules settle down on the plate and they will not move. They are very firm and rigidly, they're sticking onto the plate, and the external friction, excessive frictional force is not there. So, that will be subsequently convected or taken away by the next layer of molecules which are moving at differential velocities. So, for the convection heat transfer, onward convection heat transfer to happen, initially, what is important is the conduction heat transfer. So, when I write that equation, Q convection is equal to Q conduction, we're right at the solid boundary, right at the initial step, where at y is equal to 0. I said y is the normal distance to the plate, and y is 0 is right on the plate. So it is the fluid conduction that happens, and because of a temperature difference, and therefore temperature variation is also in the y direction. So convection is equal to conduction at y is equal to 0, and the same heat is subsequently convected with the different molecules right on the top at various y distances. And therefore, if you have to define heat transfer coefficient, from here it is conduction heat transfer. What is Newton's law of cooling? Q is equal to HA delta T. That's equal to Ka dt by dx. A gets cancelled, and therefore H is equal to this. So very broadly, we can talk about it. So here we have to talk about local and mean heat transfer coefficients. local and mean heat transfer coefficients for a surface. So how do I say, what do I say about local heat transfer and mean or average heat transfer coefficients? So give me a minute, I'll try to draw a picture and try to explain. When there's a plate like this, a horizontal plate, when a fluid is flowing, now I say this is the leading edge where x equal to 0, this is a trailing edge where x equal to L. So x equal to 0 is where the fluid is first approaching the plate and it continues to flow over the plate. I said all these kinds of velocity variations right on. Now please remember your y direction is this. Y direction is normal to the plate. So at different y directions as you move away from the plate, if this is the plate, I'm talking about y direction this. So my finger is talking, indicating the y direction, upward movement. So as you move away from the plate, there can be velocity variations. Now, what am I talking about? Local heat transfer coefficient and average heat transfer coefficient. Now, at any happening. Now, the fluid patterns continue to change as they move along the plate, and therefore, the convection heat transfer coefficients will be different at different locations. And you will appreciate it as we discuss the laminar turbulent concepts of bound. If I come to know what is the convection heat transfer initially happening between the solid and the fluid later, subsequently, how much it is happening at a distance x, and by that equation, if you calculate, I call it as Hx. Is it appearing like K? Hx. What do this is trailing edge. This is trailing edge. So from the leading edge at various x distances, the local heat transfer coefficient or heat transfer coefficient at any given x will be different. So it varies with x. Now, what do I mean by local heat transfer coefficient? Local heat transfer coefficient is at one particular x value within the solid domain, or the heat transfer coefficient that happens, I call it as local. What do I mean by mean heat transfer coefficient or average heat transfer coefficient? In first go, I say, what is the average heat transfer coefficient? I say heat transfer coefficients are different at different x values, right? As the x is varying, heat transfer coefficients vary. Now, I calculate all these values at different x values and get the average. So that is the average heat transfer coefficient. Now, when I talk about average heat transfer coefficient, I am talking about at an average what is the heat transfer coefficient prevailing over the plate. At the leading edge it may be smaller, at the trailing edge it may be value. So that talks about at an average what is the heat transfer coefficient prevailing. Now, if you want to calculate heat transfer happening over the entire plate, you should take H average of L. Now you should understand why I used L there into A into T of the plate minus T infinity that of the fluid. TW stands for wall temperature. And H average, just now I said it is the average over the entire length of the plate. Now what is this L? L indicates till what length you have taken the average. Maybe if you are not understanding what is said, let me say, take the plate once again, and let me say, I have calculated at x equal to x1, some x value, I have calculated h, hx. This is hx1, right? Now, if I want to know what is the average heat transfer coefficient over this, in the hatched region, in the first region between x equal to 0 and x equal to x1, I say that is the average. Now you calculate all local heat transfers and get average up to x1. You get h x1 bar. So the average heat transfer coefficient is h bar, but it is not till towards the end. It's not towards the trailing edge of the plate. So when I say you can calculate the average to the portion of the plate, the portion of the length of the plate, or over the entire length of the plate. When you are getting the average of the heat transfer coefficient over the entire length of the plate, you call it as HL bar. Whereas if you're calculating average heat transfer coefficient over a particular distance, a portion of a length, then you have to indicate it as the location up to which you have calculated the average. Now I tried to explain the local heat transfer coefficient and average heat transfer or mean heat transfer coefficient. What is the difference? Probably all of you understood by now. Local heat transfer coefficient refers to a particular location at a particular x value. What is the heat transfer coefficient? Prevailing from x1 to x2. Maybe you can have x1 here and maybe you can have x2 here. In between these two places, you can get in this between these two locations, you can also get H average. So I tried to explain to you the local heat transfer coefficient and average heat transfer coefficient. Normally, the average heat transfer coefficient is given by 1 by L of integrating. Hx is local heat transfer. That's what I said. Integrating between the limits 0 and L, right from leading edge to the trailing edge. You integrate, meaning you sum up all the local heat transfer coefficients and divide overall with L. Or maybe if you are integrating surface integration, H local into DAS, area ranging from A equal to 0 to A equal to AS and 1 by AS. So it's area integration or length integration, whatever you can decide, but this is quite popular and easy, and therefore this is the equation people use it. Just now, I was talking to you about the dimensionless numbers. I was talking to you, I introduced you the Biot number and the Fourier number. Now, let me introduce one more dimensionless number called Nusselt's number. And have you seen this equation for Nusselt's number that I have given here? It is HLC by K, where L is the characteristic dimension. Right. Now, the same formula we have used for Biot number 2. Same formula we have used for Biot number 2. There is a difference between that, and therefore I draw your attention. And by definition, Nusselt's number is the same definition, whatever we have used for Biot number, we are going to use. It is the conduction resistance to conduction resistance. Conduction resistance to convection resistance. But the difference is, Nusselt's number talks about the conduction resistance and convection resistance within the fluid itself. Don't get confused. Both resistances it talks about within the fluid itself. Whereas, if you may recollect, the Biot number, how I have defined, it is defined as the internal resistance to external resistance. What was the internal resistance? It was the conduction resistance within the solid. Right. What was external resistance? External resistance was the convection resistance taking place outside. Now, though Nusselt's number is also defined as conduction resistance to convection resistance, but these two resistances belong to the fluid itself, the fluid that is participating in the convection heat transfer. Right? Now, when Biot number, you remember those lumped bodies, I said this is a solid, this is a fluid. And initially it was conduction inside the solid and therefore convection outside the solid, right? So we have drawn two resistances, thermal resistances. This was a conduction resistance. Where it was happening, what was it? It was the resistance recorded by the solid, right? Resistance belonging to the solid. So that was the internal resistance. That's why I said it is internal resistance. And convection is happening outside the solid on the surface, and therefore I call it external resistance. So, Biot number is comparing between internal and external. right? So, part number talks about the solid resistance to, convection resistance. Whereas, in this case of Nusselt's number is also HL by K. What is this? L by Ka, which is conduction resistance, divided by 1 by Ha, which is a convection resistance. So effectively, it is HL by K, right? This is what we have seen. A gets cancelled and therefore H goes onto top. HL by K it becomes. Now, when I am talking about Nusselt's number, please remember, irrespective of whatever is the solid that is used, don't worry whether the solid is copper one or iron one or brass one, aluminum one. Convection is a surface phenomenon. Please leave it to that discussion. So, when convection is happening, I said those no slip condition molecules initially participate in convection heat transfer. They take the heat. From there, it convects heat onto top. And in between also, even when the molecules are moving and the fluid particles are moving, they can collide with each other. And therefore, when heat is removed from this plate or vice versa, when heat is given to the plate from the fluid, depending on which temperature is higher, it is because of conduction and also because of convection. So both the things contribute for the heat transfer to take place. Okay. So when this is happening upward, now some heat is removed from the plate and some heat is transferred from the plate because of the participation of the fluid medium in the convection heat transfer. So now I am interested, how much of heat is removed from the plate by pure convection? What do I mean by convection there? All particles physically coming to the plate and acquiring the heat going up. Bulk motion of the molecules. How much of heat is getting carried due to bulk motion of the molecules, and how much of heat is moving upwards into the fluid domain because of the intermolecular collision or intermolecular interaction. So this is convection heat transfer. So when I am talking about Nusselt's number, I talk about the resistances offered for conduction to convection, right? So if it is a highly viscous fluid, the conduction resistance may be less, whereas convection resistance may be more. Okay, so for all gases, no, conduction resistance is very, very high, whereas convection resistance is less. So it depends. It depends what it is, right? So don't get confused between them. Two things I just draw to your attention. Biot number always compares a solid resistance to the fluid resistance. Fluid is outside the solid. Conduction resistance to convection resistance, but conduction inside a solid, convection outside the solid. Whereas when we talk about Nusselt's number, I'm sorry, I'm taking too long a time on this, but this is one aspect. I have handled the subject number of times. Many of my students went wrong. With a small twist in the problem, they always got confused to calculate Nusselt's number, because the equation is quite simple, but the concept is, you are comparing the resistances only in the fluid domain. So conduction resistance is that of the fluid, convection resistance is also that of the fluid. To confuse you, the problem can be like this. Air is flowing over a plate, let me say, he may state. Air is flowing over a plate at a temperature of say 30 degrees centigrade, and its thermal conductivity is Ka, okay, and its length is so much, that may begin. It is flowing over say copper, it's flowing over copper, let me say. He will also give the thermal conductivity of copper. Now, when you want to calculate Nusselt's number, the equation for you is HL by K. Now, H is here, whether you estimate it or it's given in the problem, and what K you substitute because it is given 2 K values. one that of the solid, one that of the fluid. Please remember, when I talk about, that's where I say, Nusselt's number exclusively belongs to the fluid. Nusselt's number exclusively belongs to the fluid. Any property that you use in this Nusselt's number equation is that of the fluid. So, Nusselt's number is HL/K. Larger the Nusselt's number, more effective the convection heat transfer is. The Nusselt's number Nu is equal to, for a fluid layer, represents heat transfer across the layer is purely by conduction heat transfer, meaning lower Nusselt's numbers, the conduction heat transfer is dominant. Now, convection in daily life, I can give you innumerable number of applications. We already discussed about it. Some of this, I said, we blow something over a hot stuff and eat it in order to cool it very quick. Okay. The air on windy day, winter days feels much colder than it actually is. Okay. So, particularly winters and summers, we should be careful about the atmospheric wind speeds. So on a windy day, the temperature, if it is say 15 degrees centigrade, it can be worse than the 5 degrees centigrade atmospheric temperature, because wind is blowing over your skin and forced convection is coming into play. Excess heat is removed from your body, because 15 degrees centigrade air can readily remove heat from your body, because your body is maintained at 36 degrees, and therefore you feel much cooler, and the feeling of colder or hotter, it depends on how much of heat is lost or gained by your body. So therefore, I have to compare two cases. One, atmospheric air at 7 degrees centigrade or 8 degrees centigrade and no wind velocity at all. In the air is just stagnant and stationary, and air is not moving. Whereas on the other case, the atmospheric temperature is 12 degrees centigrade and wind is moving at a moderate speed of say 3 meters per second kind of a speed. Now quite naturally, the second case is going to be worse, because though the temperature is higher there, the higher wind speeds allow you to remove. The applications of fans, etc., are there. Now, viscous versus inviscid regions of flow. Viscous flows are the regions where the viscosity effects are felt. Yesterday, I was talking to you about the velocity. As I said, every fluid molecule is moving at a free stream velocity. So that region appears to be behaving as if it is independent of the viscous effects of the plate, and therefore, inviscid region of flow, the velocity will be more or less constant. In the viscous regions, the velocity variations are external versus internal flows. Any flow that happens on top of a surface, we call it as external flow. Internal flow is a flow through a conduit or a pipe or a duct where it has a closed boundary, and within that closed boundary, the fluid is made to move. That we call it centralized air conditioner. All these cases come under internal flows. Anything that happens in atmosphere, wind blowing over the road, wind blowing over the roof terrace of a building, a wind moving on the along the wall of a building. All these come under external flows. So water flow in a pipe, I said, is an internal flow. Flow of liquids in a duct is called, even open channel flows can also be discussed, like the irrigation water flow channels. So it can be, it's partially, the upward cover, the top cover is not there, remaining, it has a fixed boundary. So there is, external flows, like, you keep a tennis ball on top of it, you blow air over it, and therefore the flow gets separated and takes a diversion and covers the entire ball and moves further. So this can be an external. compressible versus incompressible fluids. Incompressible flow, if the density of the flowing fluid remains nearly constant throughout, I call it as incompressible flow. But most of the fluids are compressible. Liquids are a little less compressible as compared to gases, and those which change the density during the flow, I call it as compressible flow. And whenever in the fluid flow region, when there is a density variation, we call it as compressible flow. And of course, you need to know about the Mach numbers. What is a Mach number? Velocity, speed of the flow divided by the speed of sound. And sonic flow for all speeds equal to the speed of the sound. Subsonic for all speeds of the flow, velocities of the flow less than the sonic flow. And for all speeds greater than the speed of sound, velocity of sound, I call it supersonic, and Mach number is for very high Mach numbers. Now, if the Mach number is a ratio of velocity of the fluid flow to that of the velocity of the sound. And that is the reason why, supersonic jets, whenever they are flying, jet appears to be somewhere, sound we hear from somewhere else. So that means the jet is moving at a speed greater than the speed of the sound, and therefore, when you spot the jet somewhere here, the sound would be trailing somewhere behind it. So that's how a Mach number can be explained. So Mach numbers, the fluid flows can be broadly classified into subsonic, sonic, and supersonic. And probably when we have discussed about this, nozzles in your applied thermodynamics, probably you must have discussed about all these fluid flows. The sonic fluid flow at the throat, subsonic at the entrance, and supersonic at the exit in a convergent divergent nozzle, right? The laminar versus turbulent flows. Now, the fluid flows, all of you are aware, straight away without taking much time, I say when fluid flows layer by layer and without great mixing, randomness in the fluid flow, I call it as a laminar. Laminar flow, in other words, is said as a very organized fluid motion, layer by layer fluid motion. To demonstrate this laminar fluid flow, normally in fluid mechanics laboratory, we do an experiment. That is, we set the fluid flow such that, it moves at very slow, low speeds or velocities, and you inject some colored ink at the center of the pipe and see the streamline of the ink going exactly through the center. A colored portion, colored ink was traveling along with the fluid exactly at the center line. So that implies that the color that is added or the ink that is added is moving highly organized. It's not randomly mixing with other layers of the fluid molecule, and it is following a particular flow path, right? Whereas if you increase the velocity, even while injecting the ink into the fluid flow, and when due to the increase in velocity, you can obviously observe the turbulence. When once a turbulence is set on, the ink that is injected into it is seen everywhere mixing with the fluid, and the color is dispersed. You can very easily see color getting dispersed into every part of the fluid flow. So such case, it flows as if, layer by layer in a fluid region. Whereas in turbulent flow, there are no rules. The fluid molecules can move in any random direction, and the randomness is the USP characteristic of the fluid flow. And in multiple directions, the fluid molecules must be moving. And transitional region is one where, initially the flow starts, getting changed from laminar to turbulent, and normally this transitional flow region, it is not a sustainable region. Certain times, it initially tends to be transitional, and so natural versus forced convection, I don't think I need to explain it anymore. So particularly, I told you the heated molecules go up. So with any human being, we are a heat engine. I told you already, sitting here 25 degrees centigrade, and the warm air vertically moves up. That's a Canadian camera. That's how the fluid molecules movement is spotted. Some of the parameters, very quickly, let me go through the steady flow. We have discussed in detail about steady state heat transfer. A steady flow also talks about, highly fluctuating, unpredictable. And the term uniform flow implies to, the constant characteristic of the fluid flow at a given location, not irrespective of the time. When you focus at one particular location, if you start observing the characteristic of the fluid flow remains the same in that location irrespective of the time. Then I call it as uniform flow. Periodic, like your periodic heat transfer, it oscillates about its mean. It deviates and again comes back after a time interval. It comes back to the original. So such flows, I call it as periodic. So that's how we talk about. So this internal flows, I'll talk to you a little later. Let me talk about external flows. This figure, I've already explained to you how the velocity variations are felt. And do you want me to explain it again very quickly without taking much time? Let me explain. That's what I said. When there is a plate, free stream velocity is coming, and the first layer of molecules sit pretty on the wall, and this is no slip condition. Velocity is 0 here, v is 0 here, where at y is equal to 0. What is y? Y is this direction. What is x? X is this. At any x you see, all along the length of the plate, from x equal to 0 to x equal to L, at y is equal to 0, v is 0. What is v? V is the velocity. Now, slowly the next layer of molecules start moving with some velocity. That next layer, I've given a brief explanation on this. So the next layer of velocity increases. So it goes on increasing. At a particular y distance, you see the velocity variations are felt. Initially it is 0. Slowly along the curve, if you see, the velocity is increasing. The velocity is now. Now let us analyze a fluid flow over a flat plate. A fluid flow over a flat plate. When a fluid flow is taking place over a flat plate, initially the free stream velocity enters into the plate. Now this pink region, whatever is plotted here, this is the region where the velocity variations are felt, like these velocity variations. And where for the first time the velocity is close to 0.99 free stream velocity, and join all the such points along the positive x direction. And whatever the curve I get is the boundary layer, hydrodynamic boundary layer. Velocity varied, and this has become free stream velocity somewhere here, where at this y distance, y1, let me say. And right at the trailing edge, it is a constant 0 velocity. Okay, it's a 0 velocity. Somewhere else I see at x equal to x2, the free stream velocity is attained at a distance of y2 from the plate. Now it was y1. Now let me say y2 is greater than y1, and within this the velocity profile can be drawn like this. So So velocity here is less than free stream velocity. So when you draw all such velocity profiles at various x locations and join all such points where for the first time the velocity is equal to free stream velocity or 0.98 times free stream velocity, then such a region is separating the entire fluid flow region into two layers. One is a free stream region and another one is a viscous region. And this region, I call it where velocity variations are felt, I call it as hydrodynamic boundary layer. Hydrodynamic boundary layer. And if you look at fluid dynamics, let me talk about Reynolds number and then go back there. Okay. Now, just now I have introduced a Nusselt's number in this class. Nusselt's number is the conduction resistance to convection resistance within the fluid. And Reynolds number is talking about the inertial forces to viscous force. It is a ratio of inertial force to viscous force. That means what? When inertial forces are dominating, Reynolds number will be high, or the opposing force, the viscous flows, viscous forces are very high for highly viscous fluids, and therefore Reynolds number will be less. So, what is this Reynolds number? Reynolds number is the ratio of inertial forces to viscous forces. Now, what is the implication of it? Organized, very organized. Now, I talked to you about inertia also. Let me explain it once again. So I said these molecules right on the top at no slip condition are sticking onto the plate. No slip condition. Sticking onto the plate. Now they are at inertia of rest. At rest, and inertia of rest is coming into picture. Now suddenly the fluid molecule in the next layer, it wanted to move, it is not experiencing the wall friction, and not a great one, because the molecule has already experienced that viscous friction between the molecules in the free stream region also, whereas but that was moving at a free stream velocity u infinity. Whereas, when I talk about the second layer of molecules, the second layer of molecule is now rubbing against a stationary molecule. That's what I was giving you an example. You were running from behind and hitting a person who's stationary, standing. You lose all your, speed. That's how, when it is rubbing against a stationary one, the inertial pull causes the molecule fluid particle which is already set on motion. Now the inertial effects are lesser, and therefore the third layer of molecule picks up a little more. Now there are two forces which are shear forces opposing the fluid motion and viscous forces opposing the fluid motion. So it is dominating the other. Is it the viscous force dominating the inertial force? The inertial force now, the inertia of motion. The molecule is at free stream velocity of u infinity. It tries to be at its own free stream velocity until otherwise it is opposed by something. So inertia of motion. So by virtue of inertia of motion, it wanted to continue with the same speed, whereas something else is pulling it. So the inertial and viscous forces are obviously coming into the picture, explaining the fluid flow pattern, and therefore both the forces needed to be understood, and therefore a number called Reynolds number came into picture, and Reynolds number talks about the inertial forces to viscous forces. So it is popularly explained as rho v L by mu for all flat plates and rho v d by mu for all internal fluid flows, where L is the characteristic dimension. I think rho v average d divided by mu, v average within the hydrodynamic boundary layer. Okay, so now I said three things. One is the Reynolds number is the ratio of inertial forces to viscous force, and the second thing is Remember, when it is low, it describes the fluid flow as laminar, meaning fluid flow can be visualized as organized motion. And just by knowing the Reynolds number, you can visualize, you can close your eyes, imagine whether the fluid rate come back. We'll continue up to 5. Thank you. So, the 38 are watching right now, maybe because it's a Sunday, entering from free stream region onto the domain of the wall. The viscous effects, all the wall friction effects are appearing to be maximum when affecting the fluid flow within the boundary layer region. So therefore, the dominant try to exhibit again the inertial forces, and inertial forces slowly start off whether it is laminar or turbulent. So initially, for certain distance of the fluid flow, the fluid flow appears to be laminar within the boundary layer, and for certain other distance after that, transfer obviously means as the x increases, the fluid flow for the first time appears to change from fluid flow appears to be changing from laminar to turbulent. We call it critical Reynolds number, and the distance we call it as critical distance. So till the flow transition taking place, I said, for all laminar flows, Reynolds number is lower. What is Reynolds number? Inertial force to viscous force. So initially, the understanding is that the inertial forces dominate viscous forces dominate the inertial forces, and therefore Reynolds numbers are kept low, and therefore fluid motion is highly laminar. Slowly, as the inertial forces pick up, the viscous forces are dominated comfortably and turbulent. Now, if you are not understanding it, fell in line, right? Not even a single deviation. Particularly at a very the viscous forces I can compare it to the fear of a teacher, fear of something, and inertial forces is your own capacity of thinking. Now you don't even think whether you can why should I break a line? You don't even think about breaking the line. And slowly, as you come to the upper primary, 7th, 8th, 9th, you still fall in line out of fear of a teacher, but slowly you start moving here and there, right? So the line is not as perfect as it was in the elementary school. And when you come to intermediate, probably is the first sign of your inertial forces dominating the viscous forces. You now tend to have less fear for the teacher, and slowly you understand everywhere. Now you don't have fear of anyone. So that that's what I said. It is not exactly a comparison to anything. It's not even an example. But if you draw an analogy, straight away rule and discipline and the teacher, slowly it comes down, and your own capacity to learn things, development of the knowledge that you need not care for anyone, probably asking you to drift everywhere. And that's the reason why you normally tend to go into a transition region in intermediate level, and then go highly turbulent in the engineering level or a degree level. Even in a turbulent region, I just need to draw a small layer right on the top of the plate, which is laminar sublayer. In every class you see, even in engineering, a few highly disciplined students. So maybe the analogy is completed there. So from the leading edge, at the leading edge, the boundary layer thickness is 0, and this y distance from viscous sublayer or laminar sublayer will always be seen within the boundary layer. So boundary layer thickness continues to increase as you move from leading edge to trailing edge. Now, wall shear stress is another parameter that we need to discuss, because whenever there is a fluid flow, obviously viscous effects are there and the frictional forces are coming into picture. Now, the Newtonian fluid flow equation, it is tau wall shear, which is a property, right? So the Newtonian fluid is better explained through this equation. Wall shear is equal to mu dou u by dou y. What is this dou u by dou y at y is equal to 0? The velocity variation in the y direction. Velocity 3001 meter square per second. Okay. So the viscosity of a fluid is a measure of its resistance to deformation, and it is a strong function of temperature. Viscosity again, like density, is linked to temperature. Viscometer, Sebold viscometer. You did some viscosity measurement experiments, maybe in first year, second year. There you must have very clearly seen that with increase in temperature, viscosity is decreasing. Okay, so viscosity is an inverse function to temperature. Now, wall shear stress. Now, right on the wall, when fluid is flowing, the viscous effects of the kinematic viscosity, rho v square by 2. Normally, half mv square is kinematic viscosity. So, the frictional force is shear stress into area. The frictional force that is acting on the wall is skin friction or friction coefficient multiplied by area called as a drag force, an opposing force for the forward motion. So the dynamic viscosity, of course, this property of dynamic bound relay. Within this region, velocity varies from free stream velocity. So the region where velocity variations are felt because of the viscous effects, I call it as hydrodynamic boundary. Thermal boundary layer. Thermal boundary layer is again almost similar to that. Let me say the wall temperature is TW. The surface temperature is TW. Let me say some fluid is traveling even before it reaches the plate. It had a temperature of T infinity. The TW is greater than T infinity, meaning it is a hot plate that is kept in the fluid flow region. Now, those fluid molecules which come in contact with the plate due to the no slip condition, they stick onto the plate. Now, there is a physical contact between them, and sooner or later, this temperature will be TW. This temperature will be TW. How much is this? TW. Contact with the first layer of molecule is very, very short, and quite naturally, the temperature will be at further lesser temperature. And finally, somewhere here, as the temperature continues to decrease, finally somewhere from the plate, the temperatures continuously decrease, and finally it reaches T infinity. Same such phenomena can be marked at different locations, and at different locations it can be different y values where it becomes T infinity. So I look at all such points and join them. This is what I call it as thermal boundary layer. Thermal boundary layer. Hydrodynamic boundary layer. So hydrodynamic boundary layer, mm right on the top of the plate. See, if this is the plate, if the air is flowing over it, region right on the plate. But still, this is very, very important. The hydrodynamic region is very, very important. Let me tell you. Initially, when the first application of fluid mechanics was, irrigation canals built during the Britishers' time, right? And then when the irrigation canals were built, people started, with all their scientific knowledge, they started measuring the discharge. The actual discharge, the theoretical discharge, what they have calculated, practically, the amount of water that is flowing through the canal was far less than the equations of continuity equation like rho AB. And people were surprised, and finally, the fluid mechanics was split into two branches. One is a theoretical fluid mechanics, another one is a practical fluid mechanics. Calculations were not anyway close to the practical values experienced. At that time, maybe early part of 19th century, now, I think 1901 or 1905, Frontal came out with this boundary layer concept. Till that point of time, the frictional effects were ignored, the boundary layer effects were ignored, and therefore they were going wrong in calculations. And when once with the boundary, so Frontal is almost treated as father of modern fluid mechanics. So the boundary layer, water factor, I just explained this to you to impress upon you that boundary layer is such an important. And boundary layer holds a small region as free stream. No variations. It's the same velocity all along. It is the same temperature. Whenever you see, you only see T infinity temperature, right? Temperature, meaning what? T infinity is greater than TW. Very hot fluid is flowing over a cold plate level, will be at relatively higher temperature for the reasons I have explained earlier, and finally, somewhere it will be T infinity. So this variation, whatever is felt, is thermal boundary. So thermal boundary layer to the free stream velocity. So hydrodynamic boundary layer thickness is called as indicated as delta H. The thermal boundary layer thickness is called as delta T. Okay. Plate and cold plate, but still the logic applied is the same that I wanted to define. So far we have discussed about Nusselt's number, which is conduction resistance to convection resistance within the fluid, Reynolds number, which is Fx, and molecular diffusivity of heat, the thermal variations. So these two things this is going to discuss. The molecular momentum, which is a viscous effect, right on the immediate plate, is kinematic resistance. I say that it is the conduction resistance to convection resistance. When convection resistance is low, transfer is small. So when denominator is low, Nusselt's number is high. When convection resistance is low, convection heat transfer is more, and when convection resistance is low, Nusselt's number is also high. Therefore, higher Nusselt's numbers indicate higher convection heat transfer. And Reynolds number, I said that it is a ratio of inertia force to viscous force, and both force, how they come into picture, I have explained. And for all low Reynolds transfer that's taking place in the fluid medium. Now, Prandtl numbers of gases are about 1, which indicates that both momentum Prandtl number is more. What is Prandtl number? Is very less. Okay. So, this is thermal, this is hydrodynamic. When Prandtl number is 1, what is it? What less than 1? What does it mean? Momentum is what? Momentum diffusion. Molecular momentum diffusion. What is in the denominator? The thermal diffusivity. So that means the denominator is more than numerator. Denominator is dominating the numerator. So in such case, what does it mean? The hydrodynamic effects are felt only to a shorter distance when your hydrodynamic boundary layer is has greater thickness than thermal boundary layer. That questions in the gate and all, what if Prandtl number is equal to 1? At when Prandtl number is equal to 1, whether hydrodynamic boundary layer thickness and how hydrodynamic boundary layer and thermal boundary layer compare. So this can be asked. Okay. So for all Prandtl numbers less than 1, delta T is greater than delta H. For all Prandtl numbers greater than 1, delta H is greater than delta T. This is delta. This is delta H. Right. So heat diffuses very quickly in liquid metals, and the heat diffusion is very high, and very slowly in oils, where viscous effects are very, very high level. So for all such viscous fluids, Prandtl number is greater than 1. For all liquid metals, Prandtl number is less than 1. So laminar turbulent flows, I think I have explained it to you. Reynolds number also I have explained it to you. The is the number at which the flow transition happens from laminar to turbulent. And I told you the equations. It is rho v L by mu. The rho's density, v is the average velocity, L is the characteristic dimension, and mu is the absolute viscosity. And the Reynolds number for a flat plate, I mean external flow over a flat plate, the critical Reynolds number value is 5 into 10 power 5. The critical Reynolds number value is 5 into 10 power 5. Whereas you must have studied the fluid mechanics subject. When fluid is flowing through a pipe, for internal flows, the critical Reynolds number is 2000. Equations, all these equations are available in your data book. You can correct it like, delta T. So the first one, delta H, is 4.91x divided by under square root REX. What do I mean by x? At any given location. Okay. So delta is different at different x values. So, but whatever x you wanted to calculate, you can use. Reynolds number also you should use to calculate. You should calculate only that x distance. What do So CFX, just now I told you that skin friction. What does X mean? X means at a given location, local skin friction coefficient. X skin friction that is given by 0.664 REX whole raised to the power minus 1 by 2. Ante 0.664 divided by under square root REX. REX is again rho Vx by mu. అంటే ఇప్పుడు ప్లేట్ ఇస్తే if there is a plate, you can calculate Reynolds number here, you can calculate Reynolds number here, you can calculate Reynolds number here. This is the characteristic dimension L, and a fluid flow direction is the characteristic dimension. So okay, these are all local numbers. Similarly, local Nusselt's number, when the fluid flows laminar, all these are applied. NUX equal to 0.332 Prandtl number power 1 by 3 and REX power 1 by 2. This can be applied for all Prandtl numbers greater than 0.6. Okay, so the thermal boundary layer thickness delta T is given in Prandtl number, and here also you can see when Prandtl number is substituted 1, delta T is equal to delta. So when Prandtl number is equal to 1, hydrodynamic boundary layer thickness and thermal boundary layer thickness are one and the same. For all other Prandtl is called Stanton number. ఇక్కడ కొన్ని కొత్త numbers, what are derived numbers in terms. Nusselts divided by Reynolds and Prandtl, we call it Stanton number. Prandtl multiplied by Reynolds, we call it as Peclet number. PEC Peclet. PECLET, Peclet. Stanton number, STANTON, Stanton number, STN. Stanton number is ratio of Nusselts to product of Reynolds and Prandtl, or Nusselts to either by Reynolds analogy or Chilton-Colburn analogy. Okay. And CFX by 2 is in a laminar external flow over flat plate. The local value, when it is multiplied with 2, you get the average value. Local value, when it is multiplied with 2, you get the average value, and this is applied, it's not a general statement. You can apply this only to laminar flow over flat plates. Meaning what? Meaning what? Now, I have a plate like this. CF average is equal to 2 CFX. Meaning what? Niki average value kavali ante you multiply this with 2, and you get what? You get average skin friction over this area. You get average skin friction over this area. Similarly, heat transfer coefficient. If heat transfer coefficient is Hx at this x, if you want average up to this x, it is Nusselt's number. If you want entire average over the entire plate, x with L. So, put Reynolds number at calculate cheyali. Reynolds number is rho v L divided by mu. Andukane ikkada Reynolds number, whenever you see, either they indicate it as Reynolds number suffix how much. Then C average of skin friction average will be 2 CFR. That means what? You take the local value here and multiply it with 2, you get flows over flat plate. So from these equations, which are very popular equations, you can calculate hydrodynamic boundary layer thickness, you can calculate skin friction. Why do you calculate skin friction? Wall shear stress. So what is wall shear stress? It is given in this equation. Already we have explained. Wall shear stress is equal to Cfx into rho v square by 2. So when once you know shear stress, tau W, multiply that with area, you calculate drag force also. So you may be asked to calculate drag force. Drag force is drag force for you is tau W into area. What is tau W? Cf. You can calculate drag force. Ultimately, your aim is to calculate heat transfer coefficient because you are solving a convection heat transfer problem. So when once you know Nusselt's number, Nusselt's number is equal to HL by K, and these characteristic dimensions keep changing from configuration to configuration. I told you, if it is a flat plate, case by case I will explain. If it is a flat plate, it is the length of the plate along the fluid flow direction is going to be the characteristic dimension. This characteristic dimension, you use it in calculation of Nusselt's number. You also use it in the calculation of Reynolds number. What is Reynolds number? Reynolds number is rho VL divided by mu. Okay, so when you are calculating, I'm sorry I'm repeating, but then I just don't want to confuse you on this. Rho Vx by mu, if it is Rex. If you are calculating Nusselt's X, it is Hx. So limiting only up to X, X is the characteristic dimension. If you are taking the entire plate, L is the characteristic. So that's how Nusselt's number is important, because Nusselt's number is normally expressed in terms of Frontal and Reynolds number. Meeku Buckingham Pi theorem and class lo cheppintaru kada. You must have, your teachers must have discussed about Buckingham Pi theorem. Buckingham Pi theorem, it talks about, when there are, in a physical phenomena, having n number of variables, using m number of fundamental units. What are the fundamental units? Mass, length, time, temperature. This 4. Mass, length, time, temperature. If n number of variables, forming using m number of fundamental units, now the n number of parameters can be grouped into n minus m dimensionless groups. That's the Buckingham Pi theorem. A physical phenomena, if it involves n number of variables, where is the force of convection? 7 parameters. They involve 4 fundamental units. మీరు ఇవన్నీ తీసుకుంటే లెంత్ యూనిట్ కనిపిస్తుంది, మాస్ యూనిట్ కనిపిస్తుంది, టైం యూనిట్ కనిపిస్తుంది, టెంపరేచర్ యూనిట్ కనిపిస్తుంది. సో 7 parameters use 4 fundamental units. Buckingham Pi theorem ఏం చెప్తుందంటే that can be grouped into 3 dimensionless groups, n minus m, 7 minus 4, 3 groups. And Buckingham Pi theorem further మనం derive చేసేటప్పుడు, dimensional analysis చేసేటప్పుడు, when we apply dimensional analysis, we express Nusselt's number as a function of Reynolds and Frontal. Now, why we ఈ 7 parameters ని 7 parameters కింద చదవకుండా, why do you study these dimensionless numbers? ఇప్పుడు మధ్యలో కొత్తగా Nusselt's number, Reynolds number, Frontal number అవసరం ఎందుకు వచ్చింది? It's because we group them in such a way that rather than the individual parameter itself, the grouping conveys more meaning. Now, it obviously conveys more meaning. When Frontal number is less than 1, greater than 1, equal to 1, you can very easily understand. I don't have boundary layer, thermal boundary layers, when Reynolds number is low, you can assume that fluid flows laminar. When Reynolds number is greater, you assume that fluid flows. Tau influence enti, V influence enti, CP influence enti. It is very difficult to understand each individual parameter, and again you need to talk about combination of parameters. So therefore, the dimensional analysis, by pi theorem, helps you in grouping all the variables, and that's how we have grouped entire force of convection into three fundamental dimensionless numbers. There may be derived numbers, like I said, the Stanton number, which is ratio of Nusselts to Peclet number, which is a product of Reynolds and Prandtl. So all this, may come, but fundamentally there are these three dimensions. Ultimate aim of the calculations will be to calculate Nusselt's number. And to calculate Nusselt's number, you need to know Prandtl number, you need to know Reynolds number. Just now I have explained for a flat plate how you can calculate Prandtl number and Reynolds number. Okay. Now, when once you know the Nusselt's number, it is H. So therefore, thermal conductivity of the fluid, which is a given property, Hex, it's a dimension, physical dimension of the plate. So Hx can be calculated. When once calculate Hx, Q is equal to HA delta T, you apply, calculate, heat transfer rate. So that's how it is solved. The drag and lift, those who study about aerodynamic actions and aeroplane movement. So if something lift force is vertical upward movement, this happens because of the pressure difference at the bottom and top of the moving body at the top and bottom. And drag force is one which is the opposing force. If it wants to move forward, how the air resistance or the fluid resistance stopping it move, because that happens because very important. Normally we talk about drag, and aeroplane flying is all explained very well with these two forces, lift and drag forces. And even for your automobiles, when they're moving on road, you should have an automobile designed in such a way that its lift forces are very less. When lift force is more for an automobile, its stability will be less on the road, because the vertical movement push will be more. So instead, a reverse lift force, upward pressure should be higher than the lower pressure, and therefore vehicle should always be connected to the road. So the lift and drag forces are very, very important to free stream value anyway, away from the surface. We have discussed all these things, right? A boundary drag is the difference in pressures at the front and back of the moving object in a fluid. So if for the movement of the vehicle. So skin friction depends on, the drag force depends on the interaction of the fluid molecules on the surface area, whereas the pressure drag depends on the front and back pressure differences. If the pressure difference is very high, and quite obviously a reverse force will be, an opposing force will be encountered by the moving object. So a drag coefficient can also be discussed. So drag force divided by half rho v square into surface area is a drag coefficient. Like your skin friction coefficient, a drag coefficient can also be discussed. For a flat plate, please remember, for a flat plate, skin friction is equal to drag coefficient. Skin friction coefficient is a drag coefficient, because for a flat plate there is no pressure difference between the front and back. Only for a blunt body for a different object. Now, if this object is moving, there can be a pressure differential between front and end. Now, when I say food is going over a flat plate, where is the pressure difference? No, absolutely you don't see a pressure difference across the plate, and therefore it is Cf is equal to Cfx. But for all other three-dimensional solids, drag coefficient is drag friction plus drag pressure. I have explained sufficiently about pressure drag as friction drag. The wake region, particularly the external flows, you come across this pressure drags. The pressure drag is the pressure difference at the front and the pressure difference, the pressure at the front and parallel. They are, attached to the solid boundary, but towards the rear appears to be separated from the body, and a wake region is created, which is a very low pressure region, which causes heavy disturbances. A reverse flow takes place, and that's why in supersonic jets, The wake at the tail, the wake they create, wake is such a strong disturbance at the end of a blunt body or a moving body that one should be careful about it. And also wake causes the pressure drag. So the pressure difference is, causing a pressure drag also. So therefore, a flow separation also I have explained. Okay. The heat transfers, local, these values I have already discussed. But please remember the property values, like, the Prandtl number, you use mu Cp by K, where mu is a property, Cp is a property, thermal conductivity of fluid is a property, and HL by K, where K is thermal conductivity, which is a property. Reynolds number, rho V L by mu, rho is a property, mu is a property. All these property values of the fluid which is participating in convection, if it is a flat plate fluid flow, shall be always estimated at film temperature. What is this film temperature? Film temperature is just the average between the surface temperature and the fluid free stream temperature. The fluid temperature ki surface temperature ki average temperature daggara we always estimate these properties like rho, mu, Cp, K, all these properties are estimated. When once you estimate properties, the procedure is you calculate Prandtl number, calculate, get appropriate equation for Nusselt's number from the data books. And if data books are not given, the Nusselt's number equation is straight away given to you. And in terms of Reynolds and Prandtl. So when once you know Reynolds and Prandtl and dividing with overall length, you get average value. Okay. So I said that the critical Reynolds number is 5 into 10 power 5 for a flat plate. All these values we have already defined. So the heat transfer coefficient equations, if it is a flat plate laminar, Nusselt's X is equal to 0.332 Re power 0.5 PR power 1 by 3. Nusselt's L will be equal to this. Okay. And turbulent, this is it. These are all local values. And to get average value, you can multiply this with 2. Okay. So these are some of the equations you can go through your data book. Reynolds number and Prandtl number product is a Becklet number, and I close flat plate discussion here. It is already 5:10. Thank you very much for your patient listening. I'm slightly disappointed at the number. Number how much? So 30, 35 probably is a dismal number. I was told the number of students registered are 3,000. But anyhow, don't worry. Today is 17th. I have another 5 days. I can complete the entire syllabus. Thank you. Take care. Have a nice day. Sorry.